Okay, so let me first start by recapping some of things that we have seen the last lecture, or actually even probably what I can say is that I can first give some reference. Sorry, I didn't give too much reference so far, right? So what I can say, okay, so as a reference for what we have seen so far for regularization by noise for ordinary differential equation and associated linear transport equation. Okay, of course there is the paper by Franco, Flandoli, Massimiliano Gubinelli, and Enrico Piola, which I gave, but as a kind of book which explain some of the things that basically I said and other ones as well is the book by Franco. These are St. Floor lecture notes. Okay, I think it's there 2011. So the St. Floor lecture notes were given in 2010, and then I think 1 year later or so the notes appeared, and they give an introduction to the topics, more or less similar line of what I try to explain here, and also giving other hints, other arguments, and so on. Okay, but I should say that regularization by noise for ordinary differential equation and associated transport equation, this has been has grown, is a topic that has grown quite a lot, and there are a lot of recent contribution and recent approach which I've not mentioned. I cannot mention because of a time restriction. Okay, so let me just mention perhaps a couple of approach without trying to give. I mean, I can give some reference. So one is okay. There is one approach by. So there is this approach that, besides this approach that I gave you by kind of the second Kolmogorov PDE, the second order PDE, there is another approach by Catelier and Gubinelli. I think the paper is 2016, so this has been published in this year, so it has been on archive, I think, since some 2 or 3 years before, which uses a quite different approach, based on certain, let's say, so-called Young integration, okay, which works also for more general processes like fractional Brownian motion, right? Right, so fractional, so-called fractional Brownian motion, which is a generalization of it's a Gaussian process, but does not need to have to be white in time, right? And also there is the approach, let me say, Roske et al. There is also Thorsten here, where they consider an approach more rather based on, I don't remember the year, I think it was in the first paper, okay, sorry, okay, 2010, something like that, right, okay. But there are more than one, there is more than one paper, I think this is the first one, where they have considered an approach which is based on Malevin calculus, which is a form of variational calculus of variation in for stochastic differential equations, right? These are all successful approaches that have been used, and unfortunately for time restriction, I cannot talk about that. But anyway, as a reading, you can use, if you want to read more about that, I think you can start with this one. These are nice notes. Okay, so now let's go on, let's move on. I want to give you I want to recall a couple of concepts, and then we move to the so-called Kraichnan model today of passive scalars, okay? Which is something which is of interest on its own, right? So let me recap, since I don't want to lose you, let me recap some concepts that we saw so far. First of all, the classical Ito formula, just because we are going to use today quite a lot. So if you have a process which is dx equal to f dt, let me write for the Ito integral, plus g dw, right? Then, and we have, let's say, phi, which is C2, okay, here, okay. Then, the phi of x is going to be grad phi of x times dx, and dx has this expression here, plus 1/2 trace of d square phi of x g transpose dt. Okay, so you remember this second order term, right? Which we have here. Okay, the other thing that perhaps I didn't say too much precisely these things yesterday. So it's about the continuity equation, stochastic continuity equation. Let me recall first of all the SDE. If you have an SDE, dx dt plus sigma of x dw, okay, where this is a Brownian motion, m-dimensional, okay, then you can, let's say on 0t times rd, and this is, let's say, w is an m-dimensional Brownian motion. Just think that m is equal to 1, just think to have first one Brownian motion if you want. We can associate the so-called stochastic continuity equation, which is the following equation here, divergence of b mu, d plus divergence of sigma mu, Stratonovich, dw. This is the Stratonovich integral, which is needed in order, sorry, I was wrong here, of course I have to put here the Stratonovich one. Okay. Which is needed in order, it's convenient to have the same form without second order correction in the formula itself, right? What's the equation stand for? The equation stands for the evolution of the mass. Let me say here this is a pathwise evolution. Pathwise evolution. What I mean by that? So for this SDE, I should have written here, but anyway, you can start, let's say, with initial condition, let's say, small x in RD, and to any initial condition, you can associate the position at time t. Okay, let me write this way. Sometimes I write this way. Okay, with the okay. And you have to be careful, of course, here because everything is a process, so this depends also on the random parameter, right? But for each omega, by the theory of stochastic flow, if everything is smooth at least, you can consider this map, okay? And so when I mean the pathwise evolution of the mass, I mean I have an initial mass mu0, okay? And then I consider mu t, which is the push forward of this map mu0 through the flow map. This is, I mean, the push forward, sometimes, okay, this notation is just to mean the push forward. And this is done omega-wise, okay? So it's like I fix a random realization of my vector field, of my random field, okay, and I consider the evolution of the mass, so the push forward of the initial condition under the stochastic flow, This one satisfies, at least formally, this stochastic continuity equation. So the main message yesterday, perhaps it wasn't too clear, but is that concerning this equation is that this equation represents the evolution of the mass, the pathwise evolution of the mass for this SD. What I mean is that this is, so if I take mu t to be this push forward, then mu t satisfy, then mu satisfy this stochastic continuity equation. Okay? One thing that, especially if you come from stochastic, perhaps you are tempted to think, you can be tempted to think that mu is the law of the process, right? So you have xt, xt is a random variable, then we take the law. This is not true. We are doing things pathwise, right? Okay. So in particular, let me see. Okay. Here, perhaps. No, here, sir. Okay. Sorry, just to find the right. Okay. So, however, we can kind of relate the law and mu, right? So, roughly speaking, okay. Well, okay. First, I want to give. Wait a moment. Right. Okay. Yes. Okay. Yes. So we can actually give the link between the stochastic continuity equation and the statistics for SDs, something that we are going to use today, okay? Take this all formal, so this is going to be true, of course, if everything is smooth, otherwise I have to yeah. Okay, so first of all, one-point motion, those one-point statistics, okay, one-point motion, okay. Roughly speaking, we can say that the law of, well, let me start with, yes, the law of xt, okay, is nothing but the expectation of mu t, okay. You can view this mu as a random measure, so you can take the expectation of this random measure, and what you get is a deterministic measure, which is the law of xt, right? In fact, this you can view, you can kind of view this, because if you test against a test function, so I'm using the notation like phi mu t as phi d mu t, okay? If I test against a test function, here, okay, now this is a random variable because I tested this, and so this is nothing but the expectation of, since mu t is the push forward under the flow, right? So this is essentially, well, okay, I forgot one point here, but let me just write it here. So this is just nothing but the expectation of phi of xt if, this I should have said, sorry, the initial condition mu0 is the law of x0, okay? You can also view this as the expectation of phi of xt starting from x integrated in the mu0 of x. Okay. Okay, there is also a relation with the two statistics, okay? The relation is as follows. If you take, if you double, so these are your measures, okay? So this is a random measure, so this is a product of these two random measures. You can take expectation. This is a measure on RD times D, sorry, RD times RD. Okay, what this is going to be? This is going to be the law of xt yt, okay, with x, y, solution to the SD from the initial condition with the initial law mu0 times mu0, okay? In fact, how you can see this? You can say, okay, well, let's test against the test function. Okay, yes? Of, sorry, where it is? This one, yes? Yes? Why this is coming? Yes, okay, so you can, if you test, okay, if this expectation, this test here is this one. Okay, now by definition, okay, let me write it here. Okay, this is the push forward, mu t is the push forward of the stochastic flow, of the initial condition under the stochastic flow. Put the question that, and then by the very definition of push forward, this is nothing but this. Okay, now this recovers this formula if you want. Okay, sorry? Sorry? Yeah, so your question is why there is no, okay, so the thing is, okay, actually you can even forget about that if you don't like, but the thing is, if you start, so the law of, there is this fact that the law of, so if I start x0 in a random way with initial condition mu0, since the equation is linear, okay, the law of xt, let me write this expression this is going to be the integral of the law of xt of x like times integrating along the initial condition, the initial law. So it's a kind of decomposition of the measure. But anyway, probably it's better to think, it's actually better to write the expression in this way, right? If you prefer. Just keep this, okay? In fact. And even here, right? So I can write this if you want, if you prefer. I can write this as the integral of the law of xtx xty mu 0 dx mu 0 dy. Okay? And again, how can you prove this? Exactly in the same way. So I test this against the test function psi, okay, then psi mu t times mu t. Okay, this is nothing but the expectation of psi of x, y. Okay, well, this is, okay, of course this is the integral, but this is the push forward, so I can say this is psi of xt of x, xt of y, mu 0 dx, mu 0 dy. Okay, which is exactly the expression that I wrote here. Okay. Sounds complicated at first if you don't see, but in a way, this is nothing, there is no concept here, no real new concept, right? This is the evolution, I'm just looking at the evolution of, at least at this level then, today. This is just the evolution of mass, random mass under this SD. The evolution is the same, I'm not doing anything new. There is no new concept, right? So if you still think of the SD, or and it's still okay. Anyway, I'm going to use this formula. That's why I've written. But what I want to say is that this is not nothing new, right? It's just a setup of convenient objects so far, right? The evolution is still the two. Okay. Another thing that I want to remark, I'm sorry that I have to do this, but hopefully we will be finished soon with these things. So in Ito form, sorry, the stochastic continuity equation, so I want to now rewrite, I recall from yesterday that the Stratonovich integral can be written as Ito plus correction, sorry, here I forgot the dt here. Okay? In Ito form, this equation, the stochastic continuity equation, looks as follows. The mu plus divergence of b mu dt plus divergence of sigma mu dw. Now this is an Ito integral, and the correction is as follows. It is 1/2. I think I cannot write in, I have to write in coordinate with indices. dxi, dxj, sigma I, sigma j, mu. dt, sorry. Okay. Okay, and so now you see this appears a second order term. This doesn't mean that the PDE is parabolic. Okay, the PDE is still the evolution of, it's a kind of transport or continuity equation. There is no regularization effect. Right? This is just a byproduct of the Ito formula, right? Because you have parabolic, we have in Ito formula with for Ito integration, you have this term here. I'm sorry, I'm wrong. Sorry, I'm wrong here because I mean in the end it will be. So it's better. I should better write. Sorry, because this is divergence of. So it should be divergence of sigma, divergence of sigma mu. It's still second order. Sorry, but there is a first order. I mean, the main the leading order here is the same that the one that I wrote in a moment. But okay. Okay. Anyway, so I wanted to say this is so there is this second order term, which however does not give a regularization. But what is nice is that if you take now the average. Okay, so if you take the expectation, recall this, the expectation of mu t is, let me start, if you don't, I mean, let me consider this case here. Let's say that we start with the initial measure, let's say that the initial law of x0 is mu 0, but if you don't like, just think that this is a Dirac delta, okay, so that everything is, this relation is true. And then what you get is the following things. Let me call this rho t. This satisfies rho plus divergence of B rho dt, non dt, equal to, so the expectation, recall that the expectation of the stochastic integral is 0, okay? So what you get is that you just get divergence of sigma, divergence of sigma rho, non dt, right? This is the classical Fokker-Planck equation, which is now, yes, this is a second order equation, right? And this is the classical equation for the evolution of the load. Of course, this you can get also not passing through the stochastic continuity equation, but okay. This is instead the second order equation. So you have the regular. This is the simple example of this is when b is equal to 0 and sigma is just equal to 1. This is just the heat equation, right? This is something for which you have regularity estimates and so on. Now this concludes the kind of part about the stochastic continuity equation. Again, this is just, so far is just a description of the SD from another viewpoint, from the viewpoint of the evolution of mass, the random evolution of mass. One thing I need to say still about, this should be really the last one, sorry, about the recall, about stochastic fact. I need the following lemma. I will write this in a relatively informal way. So let me assume that X is a d-dimensional process, which takes the form f dx f dt plus g dw. Now this is, I mean, I want to assume that this is vectorial. I need to assume this. So let me write this as, so g is r d goes, no, sorry, d goes belongs to R d times m, and w is an m-dimensional Brownian motion. So you can write this. This is just a vector. This is just a matrix vector multiplication. So this is nothing but the sum over k from 1 to m of the column gk times dwk, where this one wk are independent Brownian motion. Okay, these are the components of the W. Okay. Okay, now what I want to say in this lemma is that there exists a this is a bit informal, right, the way that I'm writing, is a d-dimensional Brownian motion, B, which may depend on X, but we don't care. Okay, not at this point, such that the X can be written as S dt plus dB here, and here I want to put the square root of G transpose. Where, what do I mean by square root? So this is now a D times D matrix. So this is the matrix D times D matrix square root. Okay. What I'm saying here for stochastic analyst is essentially that, so the G, I can view this G as basically the quadratic variation. Sorry, the G square, G transpose as the quadratic variation. And I'm just saying essentially that I don't care about the exact form of the G, but I only care about the quadratic variation, right? Okay, so the point is I don't care exactly how I write, which exact G here I have. This is the main point of the lemma. I just care about these things here. And this does at first seems something which is not important, but it plays a role. It's a bit technical, but it plays a role. This ends, luckily, the preliminary on stochastic part. The Kreiknan model. Okay, questions so far? Yes.
What is the conclusion here?
What's the conclusion? Yeah. There is no conclusion. So this is just to make, I mean, so far, I mean, this is just to make the point, to link this, the law of the two-point motion with this product mu t, right? This is just a convenient way so far. We will use this fact to show something about the Krajcman model, right? So I'm sorry, yes, I'm sorry that I have to put a lot of tools so far, but this is not, this is, will be convenient then to see this in the Krajcman model. Yes? No, it's enough to, okay, I didn't want to, so it's enough to be positive semi-definite in a way, which should be the case, right? So it's, you don't need to be strictly positive. I'm not sure that was the question, but you don't need, that doesn't need to be strictly positive, right? Okay, you will see this in action. So by now, this is just seems to be a technical tools, and it is actually, but you will see this in action. So okay, Krajcman noise. What we want to do this here today, okay. So far we have seen situations where the drift is irregular, and we add noise term to regularize. For certain reason, well, there are many reasons to do so. You want to do something else, or we want to do today something else, right? Which is to forget about the drift and concentrate on this term, allowing sigma now to be irregular. Okay? This may sound a mess, especially if you've not seen stochastic differential equation, but the point is there are at least two reasons to do so. Okay? One reason, as I will explain in a moment, is that this is a toy model, but nice toy model, and I will show you why, for turbulent behavior, turbulent transport. Okay? The fact that it's white in time, it makes it nice, and then you can play with no smooth sigma in a way, because you can do computation. Hopefully you will see these things in action also. There is a second reason, which is perhaps more related to regularization by noise, but we have not seen yet, but perhaps right now you can believe me, and then I will explain you tomorrow, hopefully, is that this so-called Krajcman noise, when sigma is non-smooth, will help in regularization of PDEs, or in particular of the two-dimensional Euler equations. I will explain you tomorrow, right? Okay, so let me start first talking in general about, not too much, but Gaussian isotropic. Well, this is white noise, white in time noise. Okay, so I want to consider here V to be a Gaussian centered vector field on times RD, D of course at least U, otherwise, with the following covariance matrix. Okay, so okay. Since this is a Gaussian vector field means that this is a vector field which is with the joint laws which are Gaussian. Center means 0, and since this is Gaussian, it is enough to specify the covariance. Okay, and what this is the following. It is white in time. Okay, and given by this form here, this matrix Q in space, where Q what is? Q is a matrix, is a D times D valued matrix. Okay, and is given in Fourier terms by the following expressions. Where I use this notation, bracket n, this is another bracket, as I think sometimes it's called Japanese bracket. Basically, the norm square just regularize it at 0, right? Okay. This is the Fourier transform, right? And alpha is a parameter so far, larger than 0. Okay. Okay. So here you have to think that you have a certain, for each point, you have a certain vector v, vtx, space-time points, which are random points, right? They are random vector fields, right? So for some realization of omega, you get one realization of this vector field. For another realization of omega, you get some. Okay, so what are the properties? Okay. Okay. Now, first of all, V is white in time. Okay. This is due to the fact, I'm sorry that I wrote here, perhaps that in time the correlation is a Dirac delta, right? So roughly speaking, okay, this means actually that V is a distribution valued. Actually, V is distribution valued. As V takes values in let's say distribution in time. Still, you can define it rigorously, but if you don't like distribution, just think it's a kind of very oscillating vector fields, right? White in times means that is it is decorrelated, so the values at different times are independent, roughly speaking. So V is divergence free. And why is that the case? Because in Fourier, okay, we have the Lyre projection in Fourier, which is I minus n transposed over n squared. Right? So in particular, you can prove as an exercise that the expectation of V Fourier times V of n times n square is actually 0. So this means this is the divergence written in Fourier, right? And then V is so-called isotropic in space. Okay? So this means that it is invariant in low under affine isometries. Okay. What do I mean by that? If you take, let's say, V, basically this means two things. V, that Tx plus x0 is equal in low of Vtx, okay, for any x0. And here I should be precise about what this means. So this equality is in low. By D I means equality is in low. And actually this is not just for an equality in low for fixed t and x, but for all t and x. So as a field. Right? The second property is that Vt gx, okay, is actually equal, again in low, to Vtx, okay, for any tx. This is true for any G orthogonal transformation. Okay. Yeah, exactly. Yeah, sure. So of course, this is all. So this is all. This is a random vector field. So the exact fact is that you say that V divergence of V is equal to 0. This is equal to 1. Okay. And so this one here, these two properties follow from property of Q, sorry. And the point is that, so like I can leave as an exercise the proof. So proof invariance, say, under, for example, under G, just using the following fact, which again follows from the Fourier transform, Q GZ is equal to G QZ G transpose, okay, for any G. Okay. I mean, you can, by now, if you don't see immediately, you can just believe about these properties. Now, one thing that is related to this, it's a bit more convenient. Sometimes it is more convenient to consider the following random field, which is the integral in time of V S x in ds, right? So you recall that the derivative of a Brownian motion is a white noise, right? Or in other words, the integral of the white noise is the Brownian motion. So this is in time is a Brownian motion. It's a Brownian motion in time for everything. Okay. And now we can ask about the space regular. So in particular, let's say W is C1/2 minus in time. Okay. Now we can ask about the space regularity of this object. V. Right? And so we see here, this we can more or less easily see from the covariance matrix. I recall you perhaps here the covariance matrix, the form of the covariance matrix, minus D minus Q alpha times E minus N transpose. Well, not easily, sorry, I should have been more careful. So you see that, you know that the decay of the Fourier transform is associated very classically to the regularity. What you can actually prove, starting from here, so you expect that, of course you expect that the higher alpha is, the higher decay you have, so the higher regularity you have. This is not surprising. What you can exactly prove is the following, that when alpha is positive, this W is C1 in space, actually even more, but okay. While when alpha is between 0 and 1, okay, this is actually C alpha minus in space. Okay. This is the most interesting case for us. Yes, with this formula, yes. Yeah. I mean, because I define the covariance matrix in this way, so the parameter alpha, in some sense, is independent on the dimension. Okay. Again, just a kind of notational remark. It is sometimes convenient to write WTX, so the integral of V, in the following form as basically the sum over K of sigma K of X WK T, where WK are independent real Brownian motion, right? And the point is to do so, however, I need infinite number of those, right? But for the moment, you can, you can think that you have a finite number if you like, and suitable sigma kappa suitable. It's sometimes convenient because then you can reduce the integration, the D of dW, then it reduces to sum over K of sigma K of X dWK, right? And this is what we saw, is exactly the stochastic integration that we saw, right? Okay, now what is important here, it is to understand better the structure of Q. Okay, I wrote Q in Fourier. But it is nice to have the structure, because as we will see in a moment, this plays a role, to understand how Q is in the physical space, right? So we have seen here, so basically the structure here of Q in Fourier is very simple. Q is just something which dictates the regularity of the field times the Lie ray projection. Let's see what this is in the physical space. It can be written in the following way. Okay. Plus Qn of X times the identity minus XS transpose over X squared. Okay. Okay. Where, so you see, okay, let me just write the full formula. Then I will explain what this is. Qii of xei and Qn of x is Qn of x. This is a scalar field. Qn of x is actually Qii of xej for j, different from I. Okay. So, yes? Yeah, deterministic, yes. Absolutely, thanks. Okay. So, basically we are saying the following. Q has basically only two components, in a way. So it has, yes. Questions? So it has a so if you take, let's say that you take x equal to E1, the first vector of the canonical basis. Then the Q of E1, okay, well, of, let's say, yes, actually, let's say lambda E1, okay. Q of lambda E1, this looks like as follows. It has a longitudinal component along the direction lambda 1, which is QL of lambda, right? And then it has a normal component along all other directions. This is basically the identity times, this is a kind of block matrix. This is the identity times Q, the normal component. Here, of course, this is 0, right? Okay. This is true actually for every isotropic Q. So Q which satisfies the relation that I've written here. Okay. This is really general. Okay. Okay, so far we have just we have a random vector field for which we have given structure of the we have analyzed the properties isotropic vector field, which with covariance matrix, which is given basically by the following form, right? Okay, it's not written. Wait more. Okay, right. You can actually compute explicitly those, but so far we will see this in a moment, right? But so far these are functions, right? Okay, now let me pass to the dynamics, right? We defined the vector field, now we study the dynamics, Clark-Kran model of passive scalars. Okay. So, the Clark-Kran model has been introduced by Clark-Kran himself in the 1968 paper, quite famous paper in 1968, which is essentially a stochastic continuity equation with zero drift and diffusion vector field V. The one, yes. Yes, okay. I wanted to say, so you can actually compute those explicitly. So what I can say, let me see what I can say here. Exactly. So if you want, in the case of, okay, it depends on whether alpha is. I will give you kind of spoiler for alpha between 0 and 1. These QL and QN are essentially x to the power 2 alpha. Okay. But what is important here is also the prefactor here. Okay, I will explain this in a moment. But yeah, that's x to the power 2 alpha. Okay. Right. So yeah. Okay. So the vector field V. Okay, which is, if you want, in other words, W dot. But okay. So this one. Yeah, okay, where W is exactly this one, is the vector field that I've written here, and you can write this, if you like, also as d mu plus sum over k of sigma divergence, sigma k mu, Stratonovich, dw. Okay, so essentially, this is the evolution, seeing that this is the evolution of the mass, so this is the evolution of mass advected by the velocity field, random velocity field, V. Okay. So which is, as I call, isotropic, white in time and isotropic. Okay? White in time, isotropic. Isotropic. Okay. This, of course, sorry, I didn't mention it on 0t times RD. Of course, let me just recall that the solution depends on time, space, and parameter omega. Okay. You can also, if you like, in the smooth case, you can certainly do, you can have a look to the Lagrangian viewpoint. Okay? So DSD is just nothing but dx equal to, let's say, formally speaking, I can write this one, x dot equal to v of t xt, okay, which more rigorously is the txt equal to Stratonovich dw t xxt, which is the sum over k of sigma k of xt. Okay, see, there is no x. Stratonovich dw. DSD that we have seen so far, right? Okay. Sorry, one thing that I should have written, sorry. The relation, of course, what is convenient to look is that this one is actually q of x minus 1. Okay. Okay, one thing which is sometimes helps is that due to isotropy and divergence free, actually here the Ito-Stratonovich correction, let me write it directly in formula. This Stratonovich integral here is actually equal to the Ito integral. So the Ito-Stratonovich correction in DSD disappears, right? This is convenient for computations. Okay. Now for alpha larger than 1, everything is smooth, so the V is 1 in space, and so there exists a unique stochastic flow x, and you have the, okay, and so you can define mu as the push forward, as the evolution of mass under this flow, right? And mu t, xt. What happens between alpha 0, 1 will be the main subject we would like to understand. But so far, let me, in the first part, try to give some properties which are true, of course, for alpha larger than 1, but let me do some computation first, kind of heuristic computations. These are rigorous for alpha larger than 1. For alpha in between 0 and 1 are a bit heuristics, but they are indication of what will happen. Okay, so first of all, one fact, which is not what I'm going to use, but I just want to recall for, is that the stochastic flow xt, when defined, is also invariant in law under orthogonal transformation. Orthogonal transformation. That is to say, if you take G orthogonal, Gx of x, t is in law equal to x t of Gx. I'm not going to use that, but this is also a nice feature. Okay. Now, I want to do the first two important computations about this Kreitmann model. I want to try to compute the 1-point statistics and the 2-point statistics. Try to write something about that. Okay, this is where you see now that this is going to be important to have this noise. 1-point motion. X. Okay. Okay. So we have seen okay, this is rigorous as if alpha is larger than 1, otherwise take it as heuristics, but can be made rigorous, and I will mention this, I think, later. So this one satisfies the SD written by this formula, right? SD, DWK. Now comes the lemma. So it is important only to compute this object. Let me write a bit informally. This is the quadratic variation. If you don't know, don't bother. What I only care is about this. Sigma k of x, sigma k of x, sorry, of xt. Sigma k of xt. Right. Should be, yeah, so let me, yes, sigma k of t. Okay. This was exactly, so as I recall you, so once I can compute this object, so this object here, I can write an SD which involves only this sum, right? I don't care the exact form of sigma k, right? That's why I do this computation. But what is that? Okay, well, this is nothing but Q of, recall that the sum over K here of sigma K of X, sigma K of Y, transpose, is nothing but Q of X minus Y, okay? I didn't show these things, I didn't show why it's true, but one can easily see that this is a consequence of the fact that Q has to be a covariance matrix, right, of this noise here, right? Okay, once you have this formula, well, this is what? This is nothing but Q of xt minus xt, Q of 0. Doesn't depend on x. And in particular, it is not difficult to show using the well, actually in Fourier transform as well. This is basically a constant times the identity. Okay? And now let's apply that lemma. Well, okay, for those of you who knows about stochastic analysis, I'm saying that the quadratic variation is the identity, x has to be a Brownian motion, right? If you don't know this, let's apply the lemma, and so we can say that a dxt is equal to the square root of C identity times dB for B a d-dimensional Brownian motion. Okay. So, okay, the square root of the identity is just the identity, so this is just this one. So x up to a prefactor C, which is constant C, which I don't care. C is a constant, positive constant. This is a Brownian motion. So the one-point motion is up to a scaling factor. This is essentially a Brownian motion. So one-point statistics are known and are uniquely determined. Let's see the two-point statistics. This is even more interesting. Yes? It depends on which equation. This is true at the level of the Lagrangian point, right? Not the... So this is the Lagrangian? Yes, exactly. No, sorry. Okay, let me, here, the point, perhaps this is, I'm not sure this solves the issue, but this, what I said is that I can write this as a Ito integral, right? So it's not, okay, so this is, okay, but this was not your point. So your point was, yes. Yes, so indeed I can write this way, that's the point. So you are wondering why this is not 0, but the correction is 0. No, because the correction is due to related to x v. Okay, if I hopefully can do, okay, no problem. Okay, the two-point motion, okay, by the way, all what I'm saying is classical. This has already been done in a certain sense, in the Eulerian sense, by Kreiknan itself in 1968. He takes the Eulerian viewpoint, so he argued directly with the mu. Okay, I'm going to be this Lagrangian, which I think is easier. In the Lagrangian case, this has been proved that it's rigorously for alpha larger than 1 by Baxendale and Harris in 1986. Okay, let's see. Okay, let's take the difference. I want to take, let's say, x and xy, so solution to the SD from x, starting from x and y in RD. And let's take the difference. Let me call this V. And of course, I can write the difference here. And I can now, unless sigma k are linear, in general, this won't be a closed equation. I mean, if you look at deterministic wise, this will not be a closed equation in the difference, right? But let's write the quadratic variation. Okay, let's take this. This, of course, is these things times the same thing, just transpose. Okay. Okay, now that's what? This is, we have sum over k, sigma k of x, sigma k, x of x, sorry, sigma k of x of x transpose, plus sum over k, sigma k of x, x, sigma k of x, y, sorry, x, y, y, okay, minus sum over k, sigma k of x, x, sigma k of x, y, transpose, minus sum over k, sigma k of x, y, sigma k of x, x, transpose. Okay, what's that? This is nothing but q of x minus x, sorry, xx minus xx, plus q of xy minus xy, plus q of xx minus xy, sorry, minus q of xy minus xx. Okay, now again, this is q of 0. One thing that you can easily prove as a consequence is that q is even. So this one, sorry, this is q of x. This one, so q is an even function. So this is just minus q of xx minus xy, which is basically v. Now you see, the quadratic variation depends only on the difference. So what we can do, again, we can apply the lemma. We can write dvt as what? As, let's say, some function g of vt itself times db for a b suitable d-dimensional, not the same one as before, but doesn't matter, d-dimensional Brownian motion. V is just the difference. I defined as a difference, right?
What is x and y? They are arbitrary?
X, yeah, arbitrary point. Yes, yes. X and y are d. Is a solution to the SD from x and y. Was that the question, or?
Yes. So what in this? Where is the v is the function of t and x?
Yes. Where? Sorry, where?
Second last line.
This one? Yes. Ah, no. So, sorry. You're right. Sorry. Very bad choice of the symbol. U. Okay. Thanks. D of u. Yeah, you're right. Thanks. So I mean, the thing is, I wanted to define d of u and then to write this. Yes, you're right. This is, yes. Thanks. Okay. Okay. And what is g here is g of x is nothing but, okay, there is a square root of q because of that, it doesn't matter. Q of 0 minus q of x square root. The thing is, this square root is actually easy to compute. Recall the form that we saw. One longitudinal component and one normal component. The square root is relatively easy. It's actually nothing but, basically, the square root of the longitudinal component stays itself, as well as the square root of the normal component. This one just stays there. These are just projections. And this one is just the square root of the scalar field. So this is q times ql of 0 minus QL of modulus of X. And similar here. Qn of 0 minus Qn of modulus of X. So you see now, this is, okay, let me just do one computation more and then I will comment, but you already see something which is quite nice and surprising and for which I'm not sure how to get similar things with deterministic vector fields. Or even random but not white in time. The difference satisfies a closed equation. Right? Now this allows for a lot of computation, but there's even more. Let's take now the distance. So modulus of u, so the norm of u, which is norm of x minus xy. Let's do the, okay, now I want to compute the SD for the modulus of u. Now this is a 1D object. How do I do? Well, I can apply Ito formula to the function phi of u, norm of u. Well, of course, this is not fully allowed because it's not a suit functions, but just believe me, I mean, you can do computations formally and then you can, to make it rigorous, in the smooth case, you can regularize the norm function and so on. I will just assume by now that this function is actually smooth, right? So if you do so, then you get the derivative of the modulus, which is the gradient of the modulus, which is u times grad u, times g of v dB, u dB, plus the second derivative, which so the second order the second order derivative, which is I minus u transpose times u square times 1 over 2u. You can check these things, okay? G, and then you have the quadratic term. Sorry, the g of u square kind of. Recall Ito formula, first order term, second order term, multiplied by kind of the square of the diffusion matrix. Okay. So now it's a matter of computations. To do this. This is a standard one, and so you can just compute it. And what you get here, so let me just write it here again, the Tu, so u times u, g of u dB, plus d minus 1 over u, qn of 0, minus qn of modulus of u dt. This is just this is just a matrix multiplication, and it's quite. This is a normal only projection on the normal component, so it is normal. Sorry for that you expect here to have just a normal component. Perhaps for time reason I will not develop the full computation, but believe me, this is just you just develop this. So just write this. Questions so far? Yes. Yes. Right, sorry, no, you're right, absolutely true. Yes, sorry. What is true is that you're right. I mean, I had in mind Q of L of 0 minus QL of X. Sorry. This one is, roughly speaking, X to the power Q alpha, some constant BL, and this is one the same. These are actually the same, Qn of 0 and QL of L, because the identity. So this one, sorry, you're right, and I'm going to use this in a more. Yes, exactly. Okay, and now, okay, this is now, it's nice because it depends only on the square, the distance. This is a priori not, but again, usual trick, let's compute the quadratic variation. Okay, and then what we see is that this is u times gu. This is now easier because it's just d-dimensional, so we don't, actually it's one dimensional, so we don't have to, this is just so basically what I'm going to say, no, sorry, no, it's not one-dimensional because this is a matrix, so this should be times U G of U transposed, okay, so you compute the square, these, kind of the square of that. And so this is again by a computation that you can verify from this form here. This just gives essentially, okay, this selects, as you can imagine, the longitudinal component, okay, not the normal one, right? And this, so it's not surprising that it comes, it should not be surprising that it comes this step here. Again, depends only on the distance. So you can have the SD, U equal to square root of QL0 minus QLU dt plus d minus 1 over U Qn0 minus Qn also of U dt. By the way, these two are the same, so these are basically C. This is the constant. Okay. Sorry, wrong. This was, of course, the B tilde, and where B tilde is now a 1D Brownian motion. So the outcome of that, the real, probably the most important feature of Krajcman model is that the distance between 2 points satisfy a closed one-dimensional SD. It's a one-dimensional Markov process, for those of you who know Markov process. Okay? One-dimensional. Closed. This is very nice because about 1D closed one-dimensional SD, one knows everything. Right? So we can do more or less there are tools like speed measure, scale function, for which basically from the coefficients we can infer basically what happens. Right? And this is the importance of the Krajcman. It's essentially due to isotropy and white in time. Right? White in time because then you can do all this computation, which otherwise you would not be allowed to do. And isotropy, well, Gaussian, isotropy, and white in time. Gaussian and white in time because you know how to do this computation in this way. And isotropy because you see you have all this nice cancellation coming in so that in the end everything depends only on the distance. Right? Of course, it's an idealized situations, but you can do this computation very easy. Okay. Perhaps I can write easier. Which of the element? Well, okay. No, of course. I mean, no. Okay. So what I should say is this is a toy model, right? So in that sense, so I mean, it's not. Of course, this is not realistic. It's not realistic because it is probably the most unrealistic assumption, rather than isotropy, are Gaussian and white, right? Usually a vector field that you find, like I remember once a theoretical physicist told me you cannot give an engineer a white in time Gaussian vector field, right? Of course, this is true, right? So of course, this is not, so the point is a toy model. Why it is going to be important? Because as we will see in a moment, I will mention this, in the no-smooth case, using computations like using the computation that we have done, you can, for example, have spontaneous stochasticity, so uniqueness but separation of particles. You can have phenomenon like what they call it's related to intermittency. If I have time, I will explain a little bit. Starting from a vector which is Gaussian but not intermittent, so this allows to test certain kind of ideas, not something that I did, it's something class that mostly the physics community did, allow to test certain kind of idea because one can do computation. Of course, this is a toy model, right? So this would be very nice to have more realistic things, but this is not. Okay. So Okay, now in the last part, I think I will not do everything, but at least perhaps I want to start. Of course, if there are questions, feel free to ask. Okay, let me now consider the no smooth case. Okay, so in other words, alpha now is between 0 and 1. Okay, this is okay. Now let me go, basically I already said, but now let me say this more plainly. Let me explain let me go back to the form of Q, sorry. So we have said Q of x is just longitudinal component times x over x squared plus normal component times I minus x orthogonal x squared. What is the form of this one? Now we can say, well, I already said, but so you can, can be done, I have written this in the notes. This is, by the way, this is, I've read this in the paper by Lejean and Raymond, but I'm quite likely they were not the first, actually, I think they were. Okay, but this you can see why you get this. It's a computation based on, well, let's say, Fourier analysis and change of variables, suitable change of variables. Not completely easy, at least at first, but if you want, perhaps later I can give more details. The form of this is the following: Q of 0 minus Q of QL of 0 minus QL of x, so to say, is roughly speaking beta L of x to the power 2 alpha plus large capital O, this one, and same for n. This is a scalar field, right? So this is same for n. This is beta n times x to the power 2 alpha plus b o capital O. Sorry, yes, capital, sorry, small o, so not capital, of course. Can actually be showed this should be capital O of x squared, but doesn't really matter. It was the one that I also mentioned before. The important point here, however, we don't care only about this, that there are some constants. We do have to care about the relation between those constants. The relation is the following, which is very important. Perhaps we won't see why it's very important, but I mean, we will see why, but we will not see the exact computation. 2 alpha d minus 1 beta. Okay? Well, how can you get this computation? Either you do explicit computations in the line of Lejean-Raymond, computations. These are integrals, right? We have to compute integrals of this object here. Integral starting from the Fourier transform of that, right? Or there is a much nicer, well, much shorter way, which is to impose the divergence-free condition on Q. Okay, that is to say, you impose the divergence of beta L x orthogonal, sorry, x to the power q alpha x orthogonal over x squared plus beta n x to the power 2 alpha identity minus x orthogonal x transpose, sorry, x squared. This actually has to be 0. If you do this computation, you get this relation here. Perhaps it's a nice exercise that you can try to do. Well, nice, I'm not sure it's nice. Okay. Space regularity I've already mentioned. So, okay. Now you see here, and this is something that we have already said, so the Q goes like 2 to the power 2 alpha. In particular, we have said that WTX is C alpha minus in space. So in particular, cannot apply the classical Cauchy-Lipschitz theorem for SD. So it is unclear. It is unclear now what's the meaning, or even the meaning of the equation itself. Not even talking about stochastic continuity equation. Okay, and so we can ask ourselves, okay, how can these are all nice computations, but can we actually prove that there exists a solution to the SD or to the stochastic continuity equation? And second, we can ask whether there is or not spontaneous stochasticity. So whether if we start two particles at the same position, whether they will stay the same or not. Okay, so in order to answer to these questions, okay, let me where I left the here. So if you want question 1, how to define is actually does there existence and uniqueness for either the SD or the stochastic continuity equation. Question 2, is there kind of particle separation? Okay, since the Cauchy-Lipschitz does not apply, we can ask if we start from x equal to y, whether this implies that xx, well, say x, y, starting at position x, the question is whether xt is equal to y, in some sense, which is not even precise. I mean, it's not, okay. Okay, so let me, so to give the full, so let me spoil the outcome a little bit. So there is a well-defined solution, unique solution to the stochastic continuity equation, okay, to the evolution of the mass. But this does not correspond, I mean, this does correspond, but this exhibits particle separation. So when you start with a mass at the point, this mass splits. Something which you don't see in well-posed theory in deterministic equation, or okay, when you see usually in deterministic theory, then you have no uniqueness, right? So we here uniqueness and particle separation coexist. But to give the full theory of that, it becomes perhaps slightly technical. Okay, so let me first do some again heuristic computations. Then let me talk about how can one prove some form of uniqueness, right? So let's say features of no smooth. Okay, so again, it's at the first I will stay at the heuristics level still, and then I will talk a little bit about how to make these things unique. So first things is the phenomenon of particle separation. Or, if you want, spontaneous. So, I mean, let me put it, spontaneous stochasticity. Okay, this means, roughly speaking, that if x and y are solutions to the SD, starting at the same position, x equal to y, then xt is different from yt for t larger than 0. Okay? Or in other words, in terms of the stochastic continuity equation, remember the stochastic continuity equation is the evolution of the mass. So, right, so mu t, so if you start from if mu 0 is equal to 0, if, right, then, sorry, the Dirac delta in some points x, let me call this x0 perhaps. Then mu t is not the Dirac delta. for all t larger than 0, right? Okay. This is something that you don't expect in the smooth case, because of course if you start with all mass in one point, the evolution of the random evolution of a path is just of one particle in a point, does not split. So you expect to have a Dirac delta. Here instead, there is particle separations. So an initial mass concentrated in a point just splits, right? So how do we heuristically show this? Well, it's essentially in the end of the story, we have to study the distance of two particles. I think I'm over time, but let me just finish very briefly this, so that I can, right? So I will just talk about this one. Okay, so given, so you just take this d of v, right? This essentially looks like, so sorry, not v. You take u, which is the difference of these two particles, x and xy, right? Xy, sorry, x and y. Okay, x minus y. Now we have seen that u satisfy the distance satisfy a closed equation, and in particular, if you now plug in the closed equation was this one. Now if we plug in u, we plug in that equation the form that we have for ql and qn, we find as follows: d minus 1 beta n v to the, u to the power 2 alpha minus 1 dt plus square root of 2 beta l u to the power 2 alpha minus 1 beta. Okay, up to lower order correction, which I will forget right now. Okay, and so basically now there are tools that allows you to say what happens. For those of you who know, you can prove that u to the power 1 minus alpha is a Bessel process of dimension d divided by 1 minus alpha larger than 2 in particular. Okay. Okay. For those of you who know Bessel process, otherwise you can basically forget about that. But now, what you can say by basically analyzing the coefficients of this equation, or by the fact that this is a Bessel process of dimension higher than 2, is that if you start, let's say, let me write it in plain words, then one can make it more precise. Let me write even something which is technically wrong, but let me write it this way. Starting at u0 equal to 0, ut becomes positive for any t larger than 0 with probability 1. Okay. So this means from this equation here that if you start with two particles in the same position, they are going to separate immediately. Okay. Right. This is something you, again, it follows by, unfortunately I have no time to show, but it follows from standard theory of one-dimensional SDs. Technically what I've written is not exactly correct, because what I should say is that when you start arbitrarily close to 0, you get away from 0. That's the exact statement, and then you have to work a little bit to say what happens when you 0 equal to 0. Perhaps I will not mention today, but okay. One exercise that you can do is the following. You can check that if you take u, the expectation of u to the power p, okay, let me take the right power, so it should be p plus 2 alpha minus 2, so it should be 2 minus 2 alpha, yes, 2 minus 2 alpha. This is actually goes like t, up to a constant, okay? Right? So if you want, in particular, if you take alpha is equal to 2/3, then you recover that the expectation of u to the power 2/3 goes like t. Something close to remindful of Richardson loop. In fact, they say, that's why the physicists say that this is the best value to take. Alpha equal to 2/3. Okay, yes, sorry for being over time. Let's stop here.